Hello, my name is Yannos Stamoulis, and I'm going to present you an algorithmic meta-theorem for graph modification to planarity and first-order logic. This is a joint work with Fedor Fomin and Petr Golovac from Bergen and Dimitrios Stilikos from Montpellier. We start by introducing the context of our work. Algorithmic meta-theorems, or AMTs in short, are mathematical theories that provide general conditions that imply the automatic derivation of efficient algorithms. The study of connections between common logical descriptions of families of problems, algorithmic techniques used to design efficient algorithms, and structural characteristics of the inputs can give rise to AMTs. In many cases, such theorems may automatically construct an algorithm for the corresponding problem, and in this sense, AMTs can be seen as algorithms that output algorithms. Logic on graphs comes to play an important role in the study of the complexity of computational problems. In fact, we care for the type of logic needed to describe its problem or graph property. The most important types of logic are first-order logic and monadic second-order logic. The first one deals with formulas in which variables and predicates concern individual vertices of the graph, while the second one allows sets of vertices or edges as variables and quantification over them. In the language of first-order logic, we can define subgraph isomorphism, but to define notions like connectivity or Hamiltonicity, we need the richer, in terms of expressibility, monadic second-order logic. Most known AMTs are formulated in the following way. For a graph class C, deciding properties expressed in FOL or MSOL is fixed parameter tractable on C. That means that there is an algorithm whose running time is a function of the size of the given formula times a polynomial on the size of the input graph. In the case of properties expressed in first-order logic, the most general result is that of Grohe, Kreutzer, and Siebert's on sparse graphs, while for MSOL expressible properties, we have the archetype of algorithmic meta-theorems, Courcelles theorem, on graphs of bounded tree width or rank width. Our problem belongs to the general and widely studied family of graph modification problems, problems of certifying whether we can modify a graph such that the resulting graph has some desired target property. Modification operations can be local modifications on the vertices and the edges of a graph, while the target property is described in terms of a graph class P characterized by structural or logical properties. We see graph modification problems from the scope of AMTs, and we notice that known AMTs can be extended to these problems. First, we observe that local modification operations can be expressed in FOL. Now, problems where the target property is FOL expressible are covered by the result of Grohe, Kreutzer, and Siebert's, while Courcelles theorem implies the tractability of the problem in the case P is MSOL expressible, and graphs in P have bounded tree width or rank width. Planarity is the typical property escaping the above pattern. It can't be expressed in FOL and has unbounded tree width. So the problem of modifying a graph to make it planar can't be directly solved by the above results. This problem, the planarization problem, has been extensively studied in the literature, mainly concerning the case where we remove vertices or contract edges to obtain a planar graph. But here we study a more general problem, the graph modification problem, where the target property is not only planarity, but also some additional property expressed in FOL. So we fix a modification operation among vertex removals and edge removals additions or contractions, which we denote by a box symbol, and an FOL sentence phi, that is an FOL formula where all its variables are quantified. And we define the problem graph box modification to planarity and phi, where we are given a graph G and an integer K, and we ask whether we can modify G by applying the given operation at most K times, such that the resulting graph is planar and satisfies the property defined by phi. As we can see, this does not describe only a specific problem, but whole families of problems. In this sense, it is a meta-problem. Here, we can see a list of properties that can be expressed by an FOL sentence, and also some examples of problems spanned by the framework of our meta-problem. So what we prove is that for every modification operation and every FOL sentence, our problem can be solved in FPT time, depending quadratically on the size of the input graph. This meta-theorem allows the automatic derivation of new algorithmic results for every possible problem spanned by the above framework. Of course, we pay for this generality. The function f in the parametric dependence on k and the size of the formula phi is enormous, and our running time does not match the existing algorithms on problems focusing only on planarization or on satisfying phi. Now, let's take a look on our approach and the tools we use to solve our problem. Our analysis heavily relies on Geifmann's locality theorem. Before presenting it, we give a series of definitions. First, we call a formula psi R local if it has only one free variable, say x, and its validity depends on the R neighborhood of x, that are the vertices at distance at most R. A Geifmann sentence is an FOL sentence that is a Boolean combination of sentences as the one shown here. The variables xi are the basic variables of phi, and basically phi is valid if there is a choice of vertices assigned to the basic variables that are sufficiently away from each other and satisfy a local formula psi h. Geifmann's theorem says that every FOL sentence is equivalent to a Geifmann sentence, and moreover, we can compute this equivalent Geifmann sentence effectively. Under the light of Geifmann's theorem, we can see that properties expressed in FOL are local, so this logic can't express global properties. Here, we also stress that Geifmann's theorem is a classic and widely used technique in the proofs of AMTs, and this is due to this, let's say, nice form of Geifmann sentences. From now on, using Geifmann's theorem, we assume that every given FOL sentence is a Geifmann sentence. At this point, we give some additional definitions that we will use in the rest of the talk. First, we define the domain of the problem. A vertex at R whose vertices are the ones allowed to be affected by the modification operation or be assigned to the basic variables of the formula. Also, given a box operation, we define a box planarizer to be a set of vertices or pairs of vertices such that after applying the box operation on them, the resulting graph is planar. A vertex at Q is box planarization irrelevant if the vertices or the endpoints of the edges of every minimum size planarizer of G are not in Q. Also, for the rest of this talk, we make the following assumption. Whenever we characterize something as small or big, we mean upper or lower bounded by a function of k and the size of phi. The proof of our main result is a hybrid of the irrelevant vertex technique and Geifmann's theorem, which we combine in a novel way. Briefly, in the irrelevant vertex technique, we aim to detect vertices whose removal does not affect the existence of a solution to the problem. We define two levels of irrelevancy. We say that a vertex set is domain irrelevant if we can safely remove it from the domain R. Also, we say that a vertex is problem irrelevant if we can safely remove it from the graph without affecting the existence of a solution. Our strategy is the following. If the tree width is bounded by a function of k and the size of phi, then we solve the problem using Courcell's theorem, since everything can be expressed in MSOL. Now, if the tree width is big enough, we detect and remove problem irrelevant vertices while reducing the domain. In what follows, we describe a series of algorithms that are subroutines of our general algorithm. We begin with the planarization algorithm of Janssen, Lokstanov, and Saurab which, given a graph G and an integer k, outputs, if exists, a VR planarizer of G of size at most k. This algorithm runs in time linear on the size of the input graph. Algorithm A2 receives as an input a graph G, two integers k and q, and a VR planarizer of G of size at most k, and has three possible outputs. First, it can report that G has small tree width. The second possible output depends on the type of modification operation. If we deal with vertex removals, it returns a vertex V of the given planarizer S that intersects every possible planarizer of G. If we deal with the rest operations, it reports that we have a no instance. The third possible output of algorithm A2 is a wall W, a grid-like graph as the one shown above, and the disk DW this wall encompasses, such that DW crops a planar graph of small tree width. The vertices inside DW are box planarization irrelevant, and S has no neighbors inside DW. The running time of this algorithm is also linear in terms of n. The most interesting part comes in algorithm A3, the finale of the pursuit of irrelevant vertices. Its input is the following: a graph G, an integer k, a vertex set R, and a big enough wall W, together with a disk DW with the properties mentioned before. This algorithm outputs a vertex set X inside the W that is domain irrelevant, and a vertex V in X that is problem irrelevant. As for the running time of this algorithm, also here the dependence on n is linear. To build an irrelevant vertex argument, we have to be aware of the fact that we may need to modify the planar graph cropped by DW in order to satisfy phi. So, to find the domain irrelevant vertex set, we find a packing of walls in W and compute the characteristic of each wall Wi in the packing. The latter encodes all possible ways a planarizer of G affects DWI, and vertices inside DWI are assigned to the basic variables of phi. We are allowed to consider such local parts of the graph, as phi is a Geifman sentence, and therefore its validity depends on the validity of local formulas. Now, among many walls of the same behavior, expressed in terms of characteristic, we prove that a vertex set X inside DW can be safely removed from the domain. Thus, having a vertex set X that is domain irrelevant, we can prove that a vertex V in X cannot be part of a solution or determine the validity of phi. Therefore, V is problem irrelevant. Now, we saw how to combine all aforementioned algorithms to the main one. We begin by setting the domain R to be all vertices of G, and then we run A1 and find a VR planarizer S of G of size at most k. As long as the tree width of the graph is big enough, we run A2. If we deal with vertex removals, we can find a vertex V in S that intersects every possible solution. So we remove V from G, reduce k by 1, and repeat. In the case algorithm A2 outputs a big enough wall W and a disk DW with the properties discussed before, we run A3 and we find a domain irrelevant set X inside the disk and a problem irrelevant vertex V in X. We remove V from G and X from R, and then we repeat the whole procedure. A small but key detail of this algorithm is that we run A1 once. Since S has no neighbors in DW, then removing X from R does not affect S. After repeating this whole procedure for a linear in n number of times, we end up with a graph of small tree width, and we solve the problem using Courcell's theorem. As for the overall running time of this algorithm, we can easily see that its dependence on n is quadratic. To conclude, we distinguish the following challenges for future research. Can we combine modification operations? For example, can we make both vertex removals and edge contractions? There is an issue with edge additions, which are quite hard to deal with, since when adding edges, parts of the graph may be relocated. Also, another challenge is to extend our results to more general properties that are not FOL expressible. For example, we have the property of graphs being embeddable in surface FOL or genus at most G. Here, edge additions are also hard. In the case of graphs excluding some fixed non-planar graph as a minor, even vertex deletion is hard to deal with. Thank you for your attention.